Hi, my name is Brandon Alexis Correpeña. Actually, I am a student master in Ciencia y Ingeniería de Materiales and the Universidad Nacional Autónoma de México in the Centro de Física Aplicada y Tecnología Avanzada. And I present my work titled Synthesis by the Wet Chemical Precipitation of Non-hydroxyapatite added with magnesium. Now a little introduction. Actually, the bioceramics are used like implants, protests, or artificial organs. One interesting art is the bone regeneration, because the mineral phase of human bodies are the principal formed by hydroxyapatite, a calcium phosphate. And this material can be synthesized by different methods like salt gel, hydrothermal, or precipitation, or others. The principal problem of the synthetic hydroxyapatite is the absence of ions that give the psychochemical properties of the biogenetic hydroxyapatite, like magnesium, sodium, zinc, and others, thanks to which the bones carry out all their process. For that reason, the need of include the ions in the synthetic hydroxyapatite. The magnesium is the second most prevalent ion in the bone and the fourth most abundant in the body. This is an important ion because the angiogenesis process is directly linked with the magnesium. Signs cause endothelial cells produce nitric oxide, resulting in the creation of new blood vessels. Also, magnesium deficiency causes a reduction in bone mineral density. The objective of my work is investigating change in the morphological, structural, thermal, and vibrational properties of the non-hydroxyapatite and hydroxyapatite with magnesium inclusions in the range of 4,000 to 12,000 parts per million, as well as the effect of the annealing process at 600 manufactured nano-hydroxyapatite and hydroxyapatite with magnesium using the wet chemical precipitation technique. I continue with materials and methods. I follow with the method published for Shohei because it's simple and it's easy to reproduce. I use in ammonium phosphate 0.6 molar, like phosphorus precursor, calcium nitrate 1 molar, like calcium precursor, and magnesium nitrate, like magnesium precursor, at 0.032, 0.061, and 0.123 molar, respectively, to synthesize all the samples. The precursor of calcium and nitrite, it's adding in solution of ammonium phosphate, drop by drop. And the reaction was keeping stirring and heating at 37.5 Celsius degrees. And the pH is equal to 9, controlled by adding ammonium nitroxide. This is monitored by pH meter. And then of the reaction, the product was left for aging treatment for 48 hours. This is because we need the crystal grow up. Then the samples was dried at 95 Celsius degrees and calcined at 600 for 3 hours. That's it in the figure 1B, and the figure 1A is the diagram of flux and the corresponding characteristics, functional groups by infrared spectroscopy, mineral composition analysis, inductive coupled plasma, phase structure analysis by X-ray diffraction, thermal analysis by different scanning calorimetry, and morphological superficie and size of the crystals by scanning electron microscopy.
Let's continue with results. And infrared spectroscopy, this spectra confirmed the presence of hydroxyapatite in all uncalcined samples. This can be seen in figure 2A. However, they also had bands of nitrate and carbonate functional groups as reaction byproducts. For this reason, the samples need an annealing process and 600 Celsius degrees. This temperature was enough to remove the additional compounds, as shown in figure 2b. Continues with sim. Figure 3 in A, C, E, and G show the semi-mesh of the calcium hydroxyapatites that exhibit a high dense flowers like structures and disappear after calcination at 600 Celsius degrees. This is in figure 4B, D, F, and H. The presence of the flake is due to the reaction byproducts that were removed by calcination. Londoño Restrepo reported that during the calcination of 4,000 to 9,000 Celsius degrees of hydroxyapatite, the crystal size increased from nano to micro. However, before the transition occurred, a coalescence phenomenon happened when crystals were still nanometric. According to figure 4, the incorporation at least of 1,100 parts per million of magnesium in the hydroxyapatite lattice affects the morphological and the crystal size samples. Sample magnesium hydroxyapatite 3, in that is figure 3H. We can see crystal coalescence forming dense microparticles that are not recommended for clinical applications. Continues with X-ray. Figure 4A show the X-ray parents for the calcined samples that exhibit rad peaks indexed using the ICDD card number 000090432 for hydroxyapatite. The pit located at 25879 corresponding for the 002 plane is signally shifted to the right, indicating a reduction of the lattice parameters. This shift indicates inclusion of magnesium in calcium sites because of their some balancing. The decrease in the lattice size is due to the smaller atomic radius of magnesium than for calcium. Figure 4b shows the patterns for the samples calcined at 600 Celsius degrees, emerging different lines such as 102, 210, 300, and 202 are evidence of recrystallization happening at this temperature. And now in the decoupled plasma, where I studied the effect of the magnesium addition on the calcium and phosphorus radii, the hydroxyapatite samples added with magnesium exhibit lower calcium and phosphorus percentage regarding to synthetic hydroxyapatite with magnesium, which is directly related to the magnesium inclusion in the hydroxyapatite lattice in calcium sites. However, human hydroxyapatite, bovine hydroxyapatite, porcine hydroxyapatite exhibit lower values than the poor synthetic hydroxyapatite. And hydroxyapatite with magnesium present, calcium phosphorus levels similar to the mammalian hydroxyapatites. Figure 3b exhibits the magnesium content in parts per million for all samples. Magnesium concentrations are between 3,626 and 11,205 parts per million. It is worth and magnesium HEP1. The samples magnesium HEP1 exhibit the closest magnesium contents to the samples reported by Londoño Restrepo. Figure 3C displays the calcium phosphorus ratio decreased after magnesium additing as a consequence of the inclusion the magnesium in calcium sites, and the figure 3D show the magnesium phosphorus ratio, and we can see that linear trend that confirms the inclusion of magnesium as I expected. And now we continue with crystalline quality and crystal size. Figure 6H. Ay, no, es la 6. Puta madre. Okay. Ah, no, sí, es la 6. A ver si no me equivoco con nosotros. Okay. We continue with crystal quality and crystal size. Figure 6A show the FWHM for the peak corresponding to 002 plane for uncalcined and calcined hydroxyapatite samples. Has a function of the magnesium content. Magnesium decreases after calcination to a crystallinity improvement while the crystal size increases. Figure 6B show the peak position for calcined and uncalcined samples for the 002 plane. Has a function of the magnesium concentration. Redshift regarding samples without magnesium was present, indicate a reduction of hydroxyapatite lattice. Figure 6C show the calculus of the crystal size by Schroeder equation. According to this figure, the crystal size of the pure hydroxyapatite without magnesium decreases after calcination. But Schroeder's equation does not consider the crystallinity quality, and combined effect has thus in studied samples after calcination. In resume, the recrystallization produced a decrease of the FWHM that does not imply change in the crystal size. At last, different scanning calorimetry. The study of the thermal events during the calcination. Figure 7 shows the different scanning calorimetry thermograms on their second derivative for samples from room temperature to 615 Celsius degrees. The scores show the endothermic and exothermic events to take place because of the heating process. The arrows show the exothermal events, and peak A located at 67 degrees Celsius degrees is the loss of surface water. Peak B in 113.8 Celsius degrees is attributed to the loss of lattice water. Peak C at 115.6 Celsius degrees correspond to ammonia nitrate orthorhombic system. Peak D, 207 Celsius degrees, belongs to the dissociation of nitrium oxide. Peak F, discomposition of magnesium nitrate. The zone located between 507 and 557 Celsius degrees correspond to the first coalescence of the hydroxyapatite crystalline, which they remain in nanometric. PG at 1610 Celsius degrees correspond to the melting point of the calcium nitrate. Conclusions. The more important points of my work are nanometric hydroxyapatite with magnesium inclusion in its lattice may be synthesized using a wet chemical process. Also, calcination at 600 Celsius degrees is necessary to eliminate non-reactive byproducts. This temperature has little effect on the crystal size, but it's okay. The magnesium content of this method range between 3,600 to 11,200 parts per million. mimicking the magnesium concentration in human bone, according to inductive coupled plasma findites. The FWHM of hydroxyapatite recrystallization is reduced. However, this does not suggest a change in the crystal size, according to X-ray diffraction studies. And the recrystallization and coalescence process that occur during calcination at 600 Celsius degrees cause change in the morphological and structural characteristics of the hydroxyapatite, which are verified by different scanning calorimetry. And it's all. Thanks for your attention.